Let's And according to our lecture schedule, we'll of course continue with NMR today, which is October 1st. Happy October. I don't know if you like candy and all the things that come with Halloween season, but here we are. So we're going to do a little more NMR, and then I'm going to start at the end of this chapter combining mass spec, IR, and NMR. Okay, so now we can definitely figure out the exact connectivity and structure because we have enough information. However, that also means we can have harder and harder questions because we have much more information at our fingertips. So that being said, I'll start showing you how these things are starting to get harder and how we're going to look at their connectivity. But I still have some background stuff to talk about. For example, splin-spin coupling. We got kind of an idea about that, and that our coupling constants, and that's what causes our splitting, and that's why they're evenly split. And that you can also have that splitting is typically through 3 bonds from hydrogen to hydrogen, but it can be 2 bonds, hydrogen to hydrogen, if they're geminal and they aren't equivalent, right? So the not equivalent part was the important part, and we're going to talk a little bit more about that today. So that being said, the Zoom chat is open if you want to ask questions that way. Grades are on Canvas for everything I've graded so far, and all the keys except for the homework are uploaded to Canvas as well. Okay, I'm going to go ahead and share my screen, and if you have any questions, go ahead and shout out. Since we are such a small class today, hope nobody's sick. Okay, I've had a couple, oh, I'm not connected to the internet, that's why. My iPad is just sitting here without a connection to it, so. There we go, I think we're starting to share. There we go. All right, so this is kind of where we let off last time. We were talking about how we could look at the splitting coupling constants and look at what our splitting was. And using the Poppel type nomenclature, that allows us to predict the number of peaks we have, okay? So A being the atom of interest, M being the atom next to it that should be coupling to it because it's within 3 bonds, and then X would be the number of hydrogens or something that are on the thing that's far enough away from A to not split it, but close enough to M to split it. And so that way we can start building up how many things should be split through this hydrogen, carbon, hydrogen, hydrogen to carbon, carbon to carbon, and carbon to hydrogen bond. Okay, so that's what we've been talking up to now. However, that's not the only thing we have available to us in an NMR. And in fact, when we start looking at things like oxygens, now it gets a little complicated because sometimes the proton on an alcohol does split through those 3 bonds, and sometimes it doesn't, okay? And it turns out it's pretty solvent dependent. And it is solvent dependent because if that proton rapidly exchanges with the solvent, then it does, it has no coupling, and it has a single sharp peak for that proton, okay? So imagine you have something that is an acidic solution, and so you have a hydrogen bondable hydrogen that can come and go off of that proton, off of that oxygen really quickly. And what happens is you have a singlet that's usually integrated to that full 1 proton, but there's no through bond coupling. So it kind of breaks that through bond rule, okay? However, if you have an intermediate, let's say you have it in a solvent like acetone, which has a little bit of water in it, so it has something that can exchange, you'll see is the oxygen peak, the hydrogen peak on oxygen, it's going to get a little broader, a little flatter, and it won't necessarily integrate to 100% of what, of that 1 proton. However, if the exchange rate is so low in a solvent, specifically like deuterated DMSO, we can actually observe the coupling through it. So And so this is all about the hydrogen bonding available to it in that solvent, and therefore it is really, really dependent on, if you have a lot of water contaminating your system, it's probably going to broaden out and exchange. If you have a really clean solvent that doesn't have any acidic protons on it, you'll probably get coupling. So we'll see this again and again. And so you have to pay attention sometimes that does it or does it not couple, and look to the solvent to say that. Like, for example, chloroform usually is acidic. There's usually a trace amount of HCl or DCl in there, and that allows it to do this very rapid exchange, and therefore it will not couple, and it will have a sharp peak. Things that have water contamination like THF and acetone, but not necessarily have an acid in them, are going to have an intermediate, and we're going to see a broader peak. But stuff like DMSO is going to typically be fairly dry, as well as have a very slow one. So let's look at that using our Poppel notation here. And so let's start with this end here. So this would be our A, and we have 3 hydrogens on there. This is our M, and we have 2 hydrogens on here. And our X is actually that OH with that, okay, sorry, I did not mute my phone, I apologize. I muted my watch, but not my phone. Okay, so in our Poppel notation here, we have to look at that hydrogen on oxygen as to will or will it not split. So if we just look at our A spot here, right here, we have 3 protons, and they should be equivalent, and they are split by the 2 protons here. So we should get a triplet for these A protons right here. Now, the M right here, it has 2 protons, which are equivalent, and it should be split into a quartet if the oxygen, the alcohol hydrogen does not split it. And in this case, what we see is we do get our quartet for the CH, the hydrogens next to the oxygen bonded system. And notice it's shifted up field. So we have this, like between 3 and 4 is a very common place for a CH2 bonded to an oxygen to be. We can see that on our table. We can also calculate that on one of our appendices that we have in there. And that's one thing we're going to do in our homework, is we're actually going to predict where these shifts are. So we expect that this first peak here, the A peak, is only going to have a triplet and is not going to be affected by whether or not that hydrogen on the alcohol exchanges or not. And so we get our nice set of triplet here. And in this case, when we see a nice sharp peak that integrates to that, we now know it is not going to be coupling. And when it doesn't couple, we know that the splitting pattern here is not going to include that hydrogen on the alcohol. And therefore, our prediction of that quartet is going to be accurate. Okay. Now, what would it look like if it was a very slow exchange and we do see the coupling? Okay. So what we're going to do that is we're going to change the solvent. Okay. So we're changing the solvent. This is the exact same compound. It's the ethanol, but we're changing it to DMSO. And in DMSO, it has a tendency to be very well bonded to it, and it does not exchange very quickly. And so as such, you know, this is actually just the DMSO itself, showing it has a little bit of proton in here. So that's the solvent. We're not worried about that. And we see that there is a peak way above 4. Okay. So this peak way above 4 is actually the hydrogen on the oxygen. Okay, because we were expecting the methylene next to that oxygen to be between 3 and 4, and we see a really messy peak there. And then we have our system here. So let's go back to our Poppel notation. And we have an A3 on this side. Our middle one is going to be the M2. And then we have an X1 right here. So if there's no coupling with oxygen, we expect to have a 3 divided by these 3 equivalent hydrogens plus a split there. So we're going to get a triplet here. And if we didn't have splitting, we should get a quartet here and a singlet here. Okay. However, we don't see that. So let's use that Poplin notation to figure out exactly what we should have. So in this case here, we have 2 protons next to 1 proton, which means this OH here should now be a triplet. Okay. And if we look here, we see a nice triplet, and this is the triplet for the OH next to that CH2. Because this hydrogen is not exchanging, it does count towards splitting. Okay. Now, we still have our triplet here, and this hydrogen on the OH is too far away to split this A peak. So this is our A right here. This is our X, one right here. And so now we have what's left is our M. So the M is being split 3 times by here, so that's going to give it a quartet. And the splitting from the hydrogens on this A have a specific coupling constant between 10 and 15 hertz is typical. Okay. Now, because we have this X and it's not exchanging, this 1 proton counts again. So now we have it split into a quartet plus, again, 1 more non-equivalent, so it's going to be split again. However, the hydrogen on this OH does not have the same coupling constant as the hydrogens on the carbon here. So we get a convoluted peak. So what it looks like here is that this is trying to split. And so what we end up with is this really unusual multiplet here. And it has everything to do with the carbons are splitting at this 10 hertz, 10 to 15 hertz. The oxygen's actually splitting about 7 hertz. And so the peaks don't line up. It doesn't look like we don't just add the 3 plus the 1 to get 4 plus 1 to get a pentet, because we have 2 different coupling constants. So the oxygen splitting it one way, the carbon is splitting it the other way, and therefore we have a very messy peak here. However, even if we don't see the right number of peaks here, by shift, we know that this is that middle peak of that ethanol because it's the one next to the oxygen. And this high up peak is now has the that is that peak from the oxygen being split twice by that M peak. Okay, notice that that OH peak shifted in acid in this chloroform. It's down about 2.55. Okay, in DMSO, because of the different exchange, it's way up here at 4.3. Okay. So OHs and NHs are prone to great shifts depending on solvent and its availability to hydrogen bond. So the CH2 peaks are only going to shift, maybe 1 or 2 ppm right here based on what you have on them, but they're not going to shift anywhere near as much as the oxygens and the hydrogens with and nitrogens with hydrogens on them. All right, questions on seeing that we can have coupling with oxygen or not. So most of the time we don't see it. However, you can select it and see it.
Can you repeat the last part, that the peaks in the middle of the
so why are there so many peaks here?
Yeah, I somewhere lost some. I'm okay. Sorry for that.
So if we were to just do it where we had a carbon with hydrogens on it on one side and carbon with hydrogens on the other side, in theory, those carbon to hydrogens would have the same coupling constant on either side of the peak splitting. Therefore, we'd end up with the 3 plus 1 plus 1. So we'd actually end up with a perfect pentet.
Yes.
However, the coupling constant for the carbons, the hydrogens on the carbon, are between 10 and 15 hertz. The coupling constant for the hydrogen on that oxygen can be between 7 and 30 hertz. Therefore, it's different. And therefore, instead of getting that perfect pentet of having 4 adjacent hydrogens, we don't get a perfect pentet because we have different coupling constants. Okay? That's so that's where, having that's why knowing the coupling constant is kind of good. You're fortunate now that you can actually probably hit a button on your NMR and it'll tell you what the coupling constant is. So, because the computer can do it very fast.
Is the tool that the computer uses to tell you the exact coupling constant, does that help prevent, because there's like an overlap in the range, right? Between 10 and 15, you could have the same coupling constant as between 7 and 30. So is it possible that they would exactly overlap?
It is possible. And I bet by changing solvents, you might be able to do it, or changing temperature. You could even get temperature to change those coupling constants. And they could, in fact, if you kept warming it up until you got that perfect pentet, you would know the temperature at which the coupling constants match. That's a different experiment, but that is theoretically possible. Okay? All right. So just like with oxygen, we actually can see them on hydrogen, the hydrogens on nitrogen sometimes. But most of the time, what we end up doing, especially in any solvent that is slightly acidic or does hydrogen bonding, what it does is it broadens out and it does not couple. Okay, but in this case here, because the solvent we're using, we actually do get some coupling. And so what I want to draw attention to is this end here, right here is going to be our perfect triplet and our triplet, I'm sorry, our quartet here and our doublet here, because we have that classic. And then it's separated by that oxygen and that carbonyl. So that ethyl group stays in its perfect splitting pattern for that. However, this methyl group over here, we would have expected if it wasn't coupling, we would have a singlet there, okay? And we do not have a singlet there. We actually have a doublet. So that means that our one hydrogen on here is actually splitting this methylene here, and we end up with, and if we measured the coupling constant here, we would see what that hydrogen on that nitrogen coupling constant would be. Now it looks a little bit smaller than the ones with the carbons we see over here. I haven't measured it, I probably should have. But what we'll see here is now we have our integration of 1, our integration of 2, our integration of 3, and our integration of 3. So what we do see is that in this case, because of solvent, the nitrogen does couple. But again, you change the solvent and you may not see that coupling at all. Okay, that's unique to the oxygens and nitrogens because of their ability to hydrogen bond and exchange rapidly with the solvent. Okay, so in your book on Appendix E, we can blow this up, and what we'll see is that that OH group can be moved all over the ppm range based on what it's bonded to or how acidic it is. So a couple things I'd want to draw your attention to is carboxylic acids, the OH up here, rarely shows up below 10. And they tend to be fairly broad and small because they do a lot of hydrogen bonding. And concentration will change that. Concentration will move that up and down because they tend to dimerize in solution to make an 8-membered ring. And when you get that carboxylic acid dimerization, it broadens the peak out of that and shifts it. Sulfonic acids, like toluene sulfonic acid, usually are very acidic, like the carboxylic acids, and show up very high. However, phenols are not as acidic, and we can get them down in the 4 to 7 range. Now, excuse me. That will shift a lot depending on what's attached to the benzene ring, okay? So you can actually influence that by moving it up and down with that. So in addition to that, if you use a concentrated solution so that you have intramolecular, if you have a complex where you can, like in phenylacetic acid, you can, not phenylacetic acid, salicylic acid, where you can actually hydrogen bond within the phenol and some other group attached to it, that can broaden it out even more. So the effect of hydrogen bonding means that you're going to shift your deshield. Your deshielding is going to be very iffy and will move back and forth. Okay. Our alcohols, again, in DMSO, they're shifted higher and they tend to split their adjacent materials. Most of the other solvents, you tend to get that exchange and are less than 4, okay? So, and again, you'll start looking for this with the three things you're looking for is shift, splitting, intensity, and integration. So when it integrates to 1 or just slightly below 1, you might start looking at those alcohols, even if they're split, especially if you're in the solvent DMSO. Okay. Now, enols are kind of interesting in the fact that they have acidic hydrogens, but they like to form in their enol form, they form a 6-membered ring, hydrogen bonding with the alcohol to the carbonyl. And so based on the acidity of that system, they move around quite a bit. So they form these 6-membered rings with hydrogen bonding here. And if you have the beta diketones that are kind of limited, they're shifted way down here in the 6 range. However, if you have linear beta diketones, those are the most acidic of the set, you can get them all the way up above 15, which is very unusual. And then by adding an electron donating group, so it lowers the acidity of that beta hydrogen, it makes the complex a little different, and it changes your position again. Water, on the other hand, moves around quite a bit. In fact, water is very solvent dependent. And I have a whole other page on where water shows up in different solvents. And unless you actually do oximes, those are kind of odd. It's an OH hanging off a nitrogen. So if we look at nitrogen compounds, again, it has to have a proton on there so that you'll see them. Just regular amines are actually a little bit below alcohols. And one of the things we have is it's a slightly less polar bond than the alcohols have. It doesn't hydrogen bond as strong, and therefore that's why they do that. The aryl amines are less basic than the aliphatic amines. That means they shift up a little bit to the same place that alcohols typically are found. And the amides are a lot less acidic. Urethanes and amines in trifluoroacetic acid tend to be protonated, as in they are quaternary ammonium salts, and they're shifted way up from there as well. And then thiol, actually that hydrogen sulfur bond is not very polar at all. Technically, it doesn't hydrogen bond because there's not a high enough polarity between the sulfur and the hydrogen, even though it looks like a hydrogen bond. And that, therefore, because of that, we have them being way down here, just basically almost on where the alcohols are, or even below. Okay. So, and those are all the different ones that do that. You can get splitting through the sulfur because it doesn't hydrogen bond, it doesn't exchange very quickly. So you typically do get a little bit of coupling with the sulfur compounds. But I don't remember what the coupling constants are, so I can't find that, sorry. Okay, questions about protons on heteroatoms. Heteroatoms being oxygen, nitrogen, and sulfur. Okay. So they move around quite a bit because of their acidity, their hydrogen bonding, and their polarization. And they shift around quite a bit depending on what solvent you have. So you can't really say, oh, like your methylene at the end of the chain is always going to be 0.9. All right, you're not going to have that easy thing to do, see that in these heteroatom systems. Okay. Now, the other thing that can happen.
I have a question.
Go ahead.
So if the solvent change, the shift according to each compound will be changed, or there will be a little difference?
Depending on the solvent, they can shift like 2 or 3 ppm.
Okay.
And so what you'll see is that, like, for example, I mean, even this ethanol case here, we saw that it shifted from, 2.5 ppm all the way to like 4.
Yes.
And that's the exact same compound, just a different solvent.
Yeah.
Okay. Okay. So now, the reason that you have the coupling between the protons is they each have half spin, right? So a proton over here and a proton over here have half spin. And so you get that spin-spin coupling, and therefore you get splitting, okay? However, those aren't only nuclei with half spin, okay? So fluorine 19 has an odd number and an odd molecular weight, and it actually has a spin of 1/2. And 100% of fluorine is fluorine 19. So fluorine tends to split these signals as well. And the crazy thing about fluorine is it can actually do more than the 3 bonds we typically see. And deuterium, it has technically an integral of 1, but it can do some splitting, but we tend to not see that very much. Phosphorus and silicon both have isotopes that do have half spin, and they can couple. And C13, even though it's naturally occurring only at 1.1%, they does show up as coupling. So what you see is what we call these little spinning sidebands or satellites. And so an example of a satellite is something like this and this and this and this. See how those little peaks are just barely about 1%, and they're evenly spaced out from our primary signal? Those are what we call satellite peaks, and those are typically found in that carbon-13. So, but let's talk about fluorine for a minute here. But in the case of this fluorine here, because it has half spin, okay, it has half spin, and it's on this atom, it's going to do a 2-bond couple, okay? Fluorine is not hydrogen, and therefore they are not equivalent, and therefore hydrogen has a half spin, fluorine has a half spin, and therefore they can spin couple, okay? Now, fluorine typically has a very big range, and we'll talk about fluorine when we talk about other nuclei in another lecture. However, the coupling constant on this 2-bond system is actually quite high. They can be as high as like 75 hertz. And so what we see here is on the carbon here that has that fluorine and the carbonyl here, we actually see it shifted, number one, way high for having 2 electron withdrawing groups on it, de-shielding it. And the coupling constant is 48 hertz, which is about 4 or 5 times higher than we would normally see with just hydrogen, okay? Now, but what we also see is this group right over here is actually this peak here, and you're going, hey, you know, there's no hydrogens on the carbon next to it. And there's, you know, there's 2 hydrogens, but those are 4 bonds away, so those are too far away. But there is a fluorine here. And the fluorine 4 bonds away still has enough of a spin-spin couple to be seen. And that spin-spin couple here is actually measured to be about 4.3 hertz. So you basically lose an order of magnitude per bond over from the 2 bond to the 3 bond is going to be closer to that of a hydrogen couple. And then with our 4th bond, it goes down again. So occasionally the single fluorine in the system will drive you crazy trying to figure out where it is. But the closer it is to the hydrogens of interest, the bigger the coupling constant is going to be. The further away 4 bonds, you can even see it occasionally on a very high field NMR at 5 bonds, because the coupling constant will still be about 1%, 1 hertz. All right, questions on coupling through other nuclei, specifically that fluorine example. So for phosphorus, silicon, and carbon, those tend to be fairly low. The natural abundance of phosphorus and silicon is higher than that of the carbon-13, but they appear to be something like satellite peaks, and the coupling constants tend to be pretty big. Okay. All right. So we're going to do more about the different nuclei in another chapter, but I just wanted to introduce that spinning band or that satellites peak that we'll see a lot here, and that's the carbon-13 one. And fluorine itself is spin active. We can do just fluorine NMR, or we can look for the coupling constants in the proton NMR as well. Okay. So when I described that molecule up there, I said we had 2 hydrogens that were equivalent attached to the same carbon, and 1 fluorine that's not the hydrogen, and therefore it's not equivalent and can't split. Okay. Now this brings us to the thing to talk about as what we call chemical shift equivalence. Okay. So when we think about equivalence, it's not just do they look, are they on the same carbon, Do they have the things same bonded to the carbon? Because of our rotation, free rotation in long chain or sigma bonds, and our rapid spinning here, we have to take into account symmetry elements to measure chemical equivalence. What I mean by that is that if you're shooting your radio frequency at a right angle here, right, and you have one of your molecules in this direction and one of them in this direction, and they just happen to be have a symmetry plane or an inversion center, then they are going to look identical even though they're in different spaces because of these different planes of symmetry, inversion centers, etc. And so I want to describe them to help you understand some of the unusual places to look for chemical equivalents. So in the first one here, we would think, okay, those are not going to be chemically equivalent because, I mean, those are going to be chemically equivalent because they're both attached to the same carbon and there's 2 chlorines on them. Okay. So this would be our classical equivalence because they seem to be identical. Okay. So, but if we change one of those groups to chlorine, okay, now we have the possibility of it saying, well, they might be different, right? However, because we can draw a plane that goes through these 3 carbon, I mean, these 3 atoms, the fluorine, the chlorine, and that, and we have a mirror plane in there, this hydrogen looks like that hydrogen, therefore they are equivalent because we can draw that mirror plane that has those 2 hydrogens look equivalent, okay? So the other thing we can see here is even in a chiral compound like this, if we draw our plane from through these carbons here, those hydrogens are starting to look equivalent again, okay? So we're starting to see that we can see a difference in them in a part of the space, but we see a difference in connectivity, but a similarity in the symmetry element of it. So, and this one's probably the hardest one to grasp here, is that this has what we call an inversion center. If we took a point in the center of this molecule here, that's in the middle of this ring here, these hydrogens will invert to each other. These chlorines can invert to each other. Hydrogens can invert to each other. These fluorines can invert to each other. And all the 4 carbons can do the same thing. So they can all swap through that center of inversion. And if they can swap through that center of inversion, that means that they can be seen as equivalents by your okay. And then when we have things like this, where we have this as a chiral center, we actually can have these 2 be the same or different because we can have this group, because we have a sigma bond here rotating around. And so occasionally you'll get an extra peak that you didn't think you had there because of these becoming non-equivalent due to their being either fixed in space like in a ring or being equivalent because of free rotation around a bond. Okay. And so there's a number of these examples where we can see it in chiral and achiral molecules. The result is that if they are equivalent, then they're going to have the same splitting. And if they are not equivalent, you're going to have different splitting. And so you need to look for that equivalency in different elements, especially things that seem symmetrical, like this. You start looking for that extra level of symmetry to see if it's going to complicate your spectra or simplify your spectrum. Okay. And the one way we can look at that is we can quote tag, which basically means keep in mind which one is which, okay? So in this case here, if we tag this one and, or we just thought of that one as the one that's then, and then we did some kind of symmetry element, where would it end up? And in this case, if we did that near plane using this to create the plane, this element would be equivalent to that. And so those are the same through that symmetry element. Now, in this one right here, we think we have a plane here, this one the same as that one. However, now we have a difference in electronics here and here, and these actually become enantiotopic, or the enantiomers, the stereo-centered ones. But that doesn't mean they aren't going to be at the same location. And then the last one is when we're one carbon off of a chiral center. Now that's where you would tend to find a diastereomer, is when you have two chiral centers in the same molecule. And if they are magnetically not the same, they are magnetically diastereotopic, because they would be different. And they would be split differently, even though they seem to be the same in a symmetry element. So this is just one little thing that can complicate things or simplify things. And most of the time, it tends to simplify things through a symmetry element. There we go. Okay. So let's take the example of that enol keto tautomerism, which we saw in the rapid exchange of oxygen, that it would show up that it can shift that appearance of that OH. Okay. And let's think about equivalent and non-equivalent structures associated with that. Okay, so in this case here, when we have it in its ketone form, right here, we don't have an OH peak, and we don't have a carbon-carbon double bond. Therefore, we only have sp3 hybridized carbons, and only have those sp3 hybridized hydrogens. Okay, so that means we should have everything in our peak, down in below 3, except for that little methylene right between the two ketones. Okay. Now, when it switches to its enol form, it's got a hydroxide on it, it's got an alkene on it, and it's got a ketone that is hydrogen bonded to that enol alcohol. Okay. Now, because of that hydrogen bonding to that enol alcohol, and the fact that it's partially bonded to that carbonyl, it's actually shifted way high, above 15 ppm. And because it's kind of held in that hydrogen bonding, it's slightly broad. Okay. And in fact, there are no hydrogens near there to have it split or not split. So we're not seeing that. Now, the group here also is going to be, number one, shifted because it has 2 electron withdrawing groups. And those should be equivalent to each other. And so we should get a singlet peak for that right here. However, in the enol form, we lose that sp3 hybridization. It turns into sp2 hybridization. And now we have it shifting up here into where we expect alkene hydrogens to be. Okay. And what also happens is that these methyl groups are not the same as these methyl groups in the 2 different forms, even though you think they'd be the same, because they're still bonded to that structure. In the ketone form, they are going to be slightly higher and equivalent. However, in the enol form, because you have this partial single bond and this partial double bond flipping back and forth, back and forth, back and forth, we end up shifting it slightly downfield from where it started. Okay. So that's another thing to look for in our system. You would expect to have 2 singlets for just that compound, but the fact that it does this enol keto tautomerization, especially in the presence of a hydrogen bonding solvent, we actually end up seeing a total of 5 peaks, 1 for each of the 2 compounds in its thing. And based on the integration of the different peaks, we can actually predict which way it's shifted. We can actually say, well, 15% of the time it's the ketone, and 85% of the time it's that. Even though it's a very symmetrical molecule, it's now having these shifts with this rapid interconversion between the two systems. Because it's rapidly converting, now we have a non-equivalent system, and we have to show both sets of hydrogens. Okay? So these are just odd things that can happen in your system, and you have to pay attention to those symmetry elements and whether or not it can convert. Okay, so in general, when we start talking about things with single bonds, you tend to have free rotation around sigma bonds, right? However, if groups get large or if groups start to attract each other, we start losing the equivalence and we end up having peaks show up at different places and or they can have different coupling constants. So for example, if we started with just a general structure here, right here, and we have A, B, and C, by shifting it from one location to the other, depending on the nature of this X and Z, our B here can be more or less de-shielded through space, depending on what our groups were. And so they could have different coupling constant and or different shapes, shifts, sorry. And most likely it's going to be slightly different coupling constant. But then again, we can rotate it around. Now, if the groups are not too sterically demanding, this happens at a time frame where we don't see it. We basically end up getting them homogenized to a single coupling constant and a single system. However, if we start to get really big groups that try to force out one or more of these configurations, for example, if we have the bromine and chlorine here, those are fairly much larger than hydrogen, okay? And so it prefers this anti-position where they're opposite each other here. So when it tries to go to the gauche position, it's going to spend less time at this gauche position than at this anti-position here. And so these two positions here, where the hydrogens are all together here, is that particular one is less common. If you average out over time, it spends less time in that configuration than this configuration. And in that configuration, your A, B, C, and D are probably going to couple where A's are going to be one coupling constant and B's are going to be the second coupling constant. Now, it gets even more complicated when you put another group on it like this, and you really are hindering free rotation. You're going to start to see each of those protons show at a different place. And in the most extreme case of this, we have an alkene where you have zero rotation. And if you have a monosubstituted alkene, all three of those hydrogens are going to have a different position and a different coupling constant. Okay. Are you starting to see how the dynamics of the system can change, right? So, which means, let's say we just had, this theoretical one here. Okay. If we did this at a high temperature, all of those hydrogens are going to coalesce into one peak. As we cool this down, depending on what the groups X, Y, and Z are, we could get 3 different peaks because we lose our free rotation. All right. So now that is the chemical equivalence based on symmetry and chemical equivalence based on modes of rotational freedom. But there's also a magnetic equivalence, especially in things that can form a toroid of electrons. For example, benzene rings. Benzene rings have that cloud of electrons above and below. And so this interacts with the magnetic field differently than things that don't have that ring of electrons. So an alkene does not react with the electric field, the magnetic field, the same way a benzene reacts with the magnetic field. And if the benzene reacts with the magnetic field, it's going to change its coupling equivalence, and we're going to get more complex spectra because it's interacting, the different components see different parts of the magnetic field, and therefore they can or cannot be equivalent, and that changes our spin coupling equivalence as well. Okay. So let's see. Yeah, and most of these things we're talking about are what we call first order spectra, which is things that are, we can see coupling constant splits above 1 hertz. Okay, so in the case of this compound here, our classical thing we learned in organic chemistry was that a para-substituted material gives us a doublet of doublets that are symmetrical with the taller parts in the middle. However, because of the magnetic non-equivalence on them, we actually see more than just those 2 peaks. We see these other peaks here, and these other peaks have slightly different coupling constants. So we have these 2 peaks right here giving us our primary coupling constant split right here. But then the fact that these are magnetically not the same as these, because this is an electron withdrawing group and this is a different group, and we have the magnetic field coming in and out of that plane, we actually have a second set of coupling constants associated with the non-magnetically equivalent system. So sometimes, especially in symmetrically substituted pairs, you'll see them, the classical doublet of doublets. However, when you have the non-symmetrical and it's in that magnetic field, you're going to get a more complex spectrum due to that second order splitting. Excuse me. Mold must be high today. Okay. So another way we can see that is in this case right here, we'd expect to see a different doublet of doublets because in theory, this A and this A should look the same, and this X and this X should look the same. However, because the idea that we have this magnetic field coming through the center of the system here, that this and this side has a slightly different influence on the magnetics than this side and this side. And so we split from our classical meta pattern to give this additional thing. Notice the coupling constant difference between the primary or first order is the big peaks here, and then we have a secondary splitting here, which is a much smaller 1 or 2 hertz that we get here. You get that secondary splitting. So most of the time we can, it just is going to tell us, give us an idea on why spectrums are dirtier or messier than we think they are. But if you really want to dive into this really deeply, we can actually go into some additional math to go. And you can do these predictions based on field strength as well. Okay. So here's another example of that, showing that with and without the different parts of this. Now, so in this case here, we have a mono-substituted benzene. So a lot of times, a mono-substituted benzene with only 1 bond to carbon gives you a single set of peaks. And it's a little messy. Okay. However, because of the idea that we have it in number 1, an extended conjugation with this system here, we have an extended conjugation, therefore we have a greater influence of the magnetic field, meaning we get a much different split from our system here. And then even our hydrogens here are split slightly differently. We're getting the doublet pattern we would expect to get from this one only being split once, this one only being split once, but this one being split twice. We see that happening as well. That's this one split by these 2, giving us that, and they're different. Sorry. So we get that splitting difference, but what we see is that magnetic component kind of sneaking in, giving us this additional splitting. So you'll see this a lot, and sometimes you can ignore it, but sometimes you have to pay attention to it. Okay, so for the most part, you look for these symmetry equivalents and magnetic equivalents. Magnetic equivalents typically are things like benzene or extended ring systems. where we see much more complicated spectrum than we expected. And for the symmetry elements, we actually can use those to get a much simpler spectrum than we expected. So things that, well, there's 3 protons here, but I only get 1 peak. We might have an inversion center or a mirror plane or something like that. And so we can keep in mind that we have those 2 different components that can affect our spectrum and maybe make it a little different than we expect it to be, but we can usually assign them based on shift and proton. And so that we can do additional, and we get most of our information from shift and integration, but we can get additional information by the symmetry and magnetic equivalence. All right, questions about that? No, it's not going to be on the quiz. No, we don't have quizzes. So, okay. All right, so now I want to work on 2 problems, and what we're going to do is we're going to look at 3 different pieces of information and try to come up with a structure. So we're going to use our mass spec, we're going to use our IR, and then we're going to use NMR to do the final system determination. Okay, so, and this is how you would kind of go back and forth with the different things to figure out what you're going to do. So the first thing is, let's look at our IR. And one of the things I liked about looking at the IR is to just kind of get an idea of what kind of functional groups we should see. So this is a time to collaborate here. What kind of functional groups do we see, or what kind of functional groups do we not see? It kind of helps us decide what to do.
OH and sp3 hydrogens.
Right, we got OH here, sp3 hydrogens. Kind of pretty baseline there. So we have no carbon-carbon triple bonds, no carbon-carbon double bonds, no carbon-oxygen double bonds. Probably don't have any nitrogens. This is a little broad for nitrogens. Remember, nitrogens would be not as strong. So we have carbons, we have an oxygen, OH, and we have hydrogens, all right? That's about what we can see here, okay? So now let's go to the mass spec. Okay. So the mass spec tells us a lot, okay? So our molecular ion peak looks like it's 93 or 95. That's interesting. Oh, wait, hold it. Our IR said we had an alcohol. Okay, alcohols occasionally lose a hydrogen during ionization. So it could be a nitrogen, or it could be just the loss of a hydrogen. But we still have a weird paranion peak. And if we look at the loss between 76 and 93, that's going to be, what is it? That's 17 or no? 18? So that's like OH or something, right? And we have another loss from 76 to 58. And that's 18. Huh. So what do we do now? What do we think we have? So we have a 28 peak, we have a 58 peak, we have that 76 peak and that weird paranion peak. What do we do? What do we do? Anybody have any ideas here? Well, let's pull up that parent ion peak here. Huh, that's a pretty interesting pattern. Anybody have any ideas what that might be?
Might be chlorine.
Might be chlorine. Okay, because what would a chlorine look like? That would be two-thirds, two-thirds and one-third, right? So it'd be a peak that looks something like that. Yeah, we got something that looks like that. So maybe there's a chlorine there, okay? Does the IR tell us anything about chlorine? Probably not, because it'd be down here somewhere. It'd be down in this region here. So there might be a chlorine there. All right, well, let's start with the premise we have a chlorine. So if we have chlorine, that's molecular weight 35, right? So just like we'll just start with a, kind of a starting empirical formula, okay? So we have, let's see, 93 minus 35 is equal to 58. Oh, that's interesting. So this gap here is 35. So that's pretty cool. So if we know we have a halogen on it, let's go ahead and figure out what our empirical formula is based on this 58 peak. So if we divided that by 13, we get about 4. So let's start with our premise that we have 58 is our peak we're going to identify our empirical formula from. So let's see, 58 divided by 13 is 4. Clear. 4 times 13 is equal to 52, which gives us 6. So we have C4, H10, Cl so far, okay? Are we done calculating our empirical formula?
No, we need to add in the hydroxyl group.
Yeah, so we need to substitute at least one oxygen. And one oxygen is 1 carbon and 4 hydrogens, right?
CH4.
That gives us C3H6Cl. Okay, O8, O. So now our working empirical formula is C3H6ClO. Okay, and we know that as a fragment, we have at least something with a Cl on it and something with an OH on it because of that OH peak, right, in the thing. And we know we have 3 carbons somewhere. So let's actually erase that. So we have a chlorine, we have an OH, and we have maybe 3 carbons somewhere. Okay. All right, so is the IR going to tell us anything else? Nope. Okay, so now let's go to our new piece of information, our NMR. Okay, and let's draw our fragments here again. We have 3 carbons, we have an OH, and we have a Cl. Oops. Right here. And ooh, this right here says we have 1 hydrogen that exchanges. So that's the OH, right? Because if it does exchange, it diminishes, gets broader. And because it's exchanging, it's probably not splitting anything, okay? So because it's a single peak and it's broad, if it was a multiplet peak that was there, we'd have to start thinking that it splits. But because it's a broad peak right here, we don't have to worry about it splitting anything. Okay, so that's the OH peak. Then we have 2, 2, and 2 protons. But we need to look at that splitting. So let's look at that splitting. Okay, so the first 2 are triplets. So this is a triplet. This is a triplet. What's that last one? Okay, so we have this broad peak here with no splitting, so it does not split with the hydrogens here. But we have this peak here, 1, 2, 3, 4, 5, quintet. Okay. So how are we going to combine 3 carbons, 6 hydrogens, an OH, and a Cl, such that we have a 2-2-2 pattern? Well, let's see. So we're not going to have any CH3s in here because we have that. We're not going to have any CHs here because we don't have anything for that. But we have CH2s. Okay.
Yes.
It must just have CH2s. Okay. Now, one of the CH2s probably has to have the chlorine on it, and one of the CH2s has to have the OH on it. Okay. So that would account for 2 hydrogens and 2 hydrogens. And we need to link them together. We only have one CH2 left. So I think that CH2 has to link these 2 together. Okay. But let's do our POPL assignment and see what our splitting should be. So if this is our preliminary structure here, I'm going to redraw it up here as OH, Cl, 1, 2, 3, yeah, right here. And let's see if we match yet. Okay, so this right here is this over here. So we got that. This right here, so this would be our A2, M2, X2. So going from this right here, we expect to have 2 protons that are split by 2 protons, giving us a total of integration of 2.
3.
Right? So we have integration of 2 in a triplet. Let's look at this X here. We have 2 protons split by 2 protons to give us a triplet. And we're going to integrate to 2 protons. So we see probably that one, because that's a triplet and that's a triplet. But what would the M be here? Okay, we have 2 protons for integration, and they are equivalent, so they're going to give themselves 1 peak, plus 2 peaks, plus 2 peaks to give us a total of 5 peaks.
Yes.
So that probably is that one there.
Around 2, yes.
Right. So our preliminary structure followed by our POPL analysis tells us that we have a consistent structure with the information given. So we took what we knew from here. This gave us the idea that we had to substitute at least 1 oxygen for the system. The mass spec told us we had to substitute at least 1 chlorine for the system. And so by taking those 2 out of the play, we knew exactly how many atoms we had left. We had 3 carbons, 6 hydrogens, and when we looked at the proton NMR, we had a total of 6 hydrogens that were not OHs. And all we had to do was figure out where to put them together. Now, by integration, we knew they were all CH2s. By POPL, we knew which carbon was which. Now, the only thing we need to assign now is to figure out which of these is the one with the chlorine on it and which of these is the one with the hydroxide on it. And how would we determine that?
The chlorine has more electronegativity, so it should be more deshielded.
So we look at our shift table and figure out which way we would see that methylene show up. And remember, on our shift table, we have a line, 2 dots, and 2 open dots, so that will tell us whether we have 3 hydrogens or 2 hydrogens or 1 hydrogen. And so we can predict from that chlorines are going to be with 2 hydrogens are going to be on average a delta of 2.8. An OH on average with 2 hydrogens is going to be a 2.5. So, no, yeah, 2.5. So that means that the lower one is probably the OH and the higher one is probably the chlorine. Okay, so see how to put all the different pieces together? So every single one of those pieces of information kind of meshes. I guess they should have been 3.5 and 3.6. All right, questions on that? Okay. I have one more example. We're going to do the exact same thing.
Sorry, I had a question.
Yes.
On the Popple notation, like I follow the A2 and the M2, but why is it X2?
So when you start, you start on one side of the molecule and move to the other. And so
Yeah.
don't confuse them. You call them different things. A is the atom of interest. So we could actually go through a Popple analysis for each and every carbon, but by assigning one of them A,
Right.
one of them middle, because that's the one that can influence it, and then one
Okay.
that can't influence our A. So we're looking at it in a way so that only A and X can influence M, only M can influence X, and only M can influence A. So we know that because of that 3-bond coupling constants, we know how many protons can, so we know only 2 of the protons on M can affect the 2 equivalent protons on A. Okay? So,
Okay, so sure, go ahead.
So we just use it to assign starting from one side of the molecule to the other, and so that we know exactly what can interact and what can't.
So in this case, it has an A, M, and X, but not every molecule would necessarily.
Correct. If you only had 2 things, you would have an A and an M.
Got
X can be an OH sometimes.
Right.
On that ethanol, I used X as the OH.
That was my confusion, and so now I see. So the A, the M, and the X in this case is just referencing the 3 the 3 pairs of protons on the carbons in the chain.
Right. The A stands for, your atom you're starting with. The
Right.
M is the middle because that's the one that can interact with either one. And then the X is the other thing. We can't call that one A2, A also, because then we'll confuse it once. So we're calling it something else.
So it is just an arbitrary orientation.
But we always start with the letters A, M, and X.
Understood.
Yes. It's, significant that X will not split A. M will split A because it's the midpoint. X is too far away.
Understood.
So
Thank you.
It's what he came up with, and it works for the most part. You just have to pay attention to which atom you're trying to analyze.
My confusion was with the OH. Thank you.
Okay. No, because, so it's any atom that has a hydrogen on it can be assigned to either of them.
Understood. Thank you.
All right, so let's go to unknown number 2.
Wait, so Dr. Irvin,
Oh, yes.
so if, say, the solvent was DMSO, it would be X3, right?
It could be, yes. And we would see, number 1, that OH peak would probably be split, at least in this case, it would be split twice. So it would be a triplet. So we would see a triplet and it would be shifted way up. It probably should be shifted up around 5 ppm. And that would change our splitting on our X on the X carbon. So those hydrogens would have a more complex splitting than just a triplet. But yes. So the first thing you'd notice is the OH peak would be a triplet, showing it's exchanging very, very slowly, and it does contribute to splitting. Okay?
So in this problem, I noticed that the solvent, at least I haven't seen it be specified. If we're going to be dealing with a difference in solvents, like if that shows up, will that be something that will be specified, or should we just look for the potential effects?
So most of the time, if it's going to play into the game, you would have, they would specify. And sometimes they even specify a temperature like 100 degrees. So that'll tell you something's going to be happening with the dynamics. But we actually know what the solvent is. Right here. Because it's the only other peak in our field, so we know what the solvent is. Anybody want to guess what that solvent is? 7.2 ppm. Oh, if you don't know where solvents show up, there's a table in your book here in chapter 3, common solvents table. is Appendix G, tells you the chemical shift in multiplicity of common solvents. And this particular one has a chloroform, deuterated chloroform, at 7.26. So I believe that small peak at 7.26 is chloroform, which is our solvent. Now, so this is Appendix G, and so where this will be showing you, if you have a little peak that's not identified, that's probably your solvent peak, and this will help you pick that. The other thing they have is where residual solvents show up in deuterated solvents. So for example, they have one for water here. So water in chloroform shows up at 1.56, but water in DMSO shows up at 3.3. And water in deuterated methanol shows up at 4.5 or 4.87. So if you have an extraneous peak, you want to look first for your G here for what your solvent is, what its multiplicity is. For example, acetone typically has 5 peaks, and it's typically in the 2 range, 2.04. DMSO typically has 5 to 7 peaks, and it's in this range as well. But then all the different solvents have different shifts that they see in different deuterated solvents. And so you can actually look at the effect of the solvent based on just common solvents, and you'll see the shifting there. So these 2 tables are helpful, especially in research, to identify extraneous small peaks to make sure they're not impurities in your system. They're just solvent or something else, okay? So there's a lot of information in this book. This is why I've kept this book forever. In fact, I even have copies of pages of this book in my lab notebook that I just refer to all the time.
So I have a question. The exchange hydrogen, that is because of the intermediate exchange or the slow exchange?
That's because it's a fast exchange.
Okay. So
Chloroform typically has a little bit of residual acid in it, and residual acid makes a fast exchange.
okay. So like it should be a small peak, not a big peak.
So it depending on how much acid is in there, if it was a lot of acid in there, it would be a very sharp single peak. But if it's a fairly low acid version, it's going to be a broad single peak. But in DMSO, it would probably be a split coupling peak. Okay, so this is pretty clean chloroform. The more water in your chloroform or acetone, the more likely it is to rapidly exchange. Okay, so let's do this one more time to make sure we have this pattern down. And the first thing we're going to look at is our IR again to kind of give us some ideas of what functional groups to start looking for and where to be. So shout out a functional group here.
Carboxylic group.
Carboxylic acid, because notice this peak goes way into below 3,000. That's classical carboxylic acid. Because your just your amide peak is going to be higher in that 32, 35, 1 or 2 peaks. The alcohol is going to be kind of around 32, but because this is centered right around 3,000, we're thinking carboxylic acid. So if we have a carboxylic acid, we should see a carbonyl group as well. And we see a carbonyl group here. Now, the fact that we have that carboxylic acid and that peak is not really shifted way down, below 12, below 1700, tells us we might have a dilute sample, so it's not like dimerizing too much. But there could be something else in the molecule that changes that. So we're expecting to see a carboxylic acid, and probably no double bonds, probably no, because there's no like 1600 here. There's not that little peak here for an NMR. So let's see what we have by, I'm sorry, the little wiggles for like a benzene ring, sorry. All right, let's look at the mass spec. Ooh, big mass, 152. and then a fragment at 73 is our major. Okay. What's the first thing we notice about the mass spec?
Bromine.
Bromine. Yeah, this is the classical bromine peak here. Okay. And because it's evenly, they're even, that means we only have one bromine. So we only have one bromine. So let's go ahead and calculate our beginning empirical formula. So what we're going to do is we're going to take our peak here and subtract out 79 from our, so we're going to take our bromine away and figure out what we have left. 152 minus 79 is equal to 73. Oh, well, we should have predicted that because this peak here. So luckily, we can look at our fragments found table and see if that's a common fragment that we should see. And our fragments found table, not fragments lost table, just found table. 73, so homologs of 59. What does that mean? Homologs of 59. So one of the things that's in there is a CO2CH3. We have an ether. We have an amide. We didn't see an amide in our IR, so it's probably not that. So homologs of that. So that might be that carboxylic acid we're seeing here. Okay. So let's go ahead and calculate out our starting empirical formula. Figure out how many carbons we have. 73 divided by 13 is equal to 5.6. So let's see. 13, so that's 5. So we have C5. 73. 65 is, that's an 8. 8 and 5 is 13, and then we know we have at least one bromine on there. Oh, wait a minute.
C5H8Br so far.
We know there are 2 oxygen as well.
Well,
Right.
5 plus 8, because there's an 8 remainder, 65 minus 30, 73 gives us 8. So 8 plus 5 is 13.
Oh, my fault.
H13Br. Okay. I don't think we're done though, because I mean, we had a carboxylic acid, which means we have to substitute.
We have C3H5.
So, okay. C3H5O2Br. We had to substitute 2 oxygens, and that's 1 carbon plus 4 hydrogens. That's a total of 8 hydrogens and a total of. So I have a working empirical formula of C3H5O2Br. Is that what everybody else has to? Okay. So, okay, that's about the information we can get from here. Let's see, we have a 45 and 55. These are losses of fragments with.
That works.
You know, these are just fragments with the bromine still on it here. So this is probably, ooh, that's an 18. So we have an OH loss as part of that. So that supports our carboxylic acid or alcohol theory. So, all right. So I think we have enough information here. Let's move on to the NMR. Okay, so first thing we see is way on the left side there, hydrogen very broad exchanges, okay? We were expecting that because of, it was a carboxylic acid. So it hydrogen bond, rapidly exchanges. What solvent are we in?
EDCO3.
Chloroform, deuterated chloroform. So we can see that. So that's also helping our exchange a little bit. And because it's exchanging, it's probably not splitting anything. So we just have 2 peaks left, and we have a total of 5 hydrogens. Okay, so that means this was 1 hydrogen, so we only have 2 hydrogens left. Okay, let's look at the splitting on these peaks. Okay. Ooh, they're both triplets. Okay, so that means we have two CH2s right next to each other. So because they're right next to each other and they're perfectly split, that means we have a CH2, CH2, but then whatever's attached here and here do not have hydrogens that split. Okay, so the things we have left are bromine and a OH. We've already accounted for this H. So what's our final compound here? We just have to hook one to one side and one to the other side and we're done, right?
Yes.
We have Br OH. Okay, let's look at our popple here. We have an A and an M, a 2, 2. So this should give us a triplet, and then this should give us a triplet with no other splitting. This is too many bonds away to split. This does exchange in its way upfield. And the bromine is not going to show us anything in an NMR. So starting with functional group, we knew what our exchanges to make in the mass spec. Our mass spec told us we had a halogen. Then we knew we had to have our halogen and our carboxylic acid somewhere in our system. Our splitting pattern in our proton NMR said we had to have two CH2s next to each other, but with nothing else splitting. Therefore, that means we had to have this as our center group, tack on the last two things. That has to be our product. Okay? Questions on that?
So it's only the chlorine that does not obey the 3 bonds away rule out of the halogens?
What do you mean? The chlorine did not split anything in the proton. The chlorine we saw because of this pattern, that 2/3, 1/3 pattern.
Oh no, I was talking about a problem we did earlier where we said that even though what was that?
It's fluorine.
Fluorine. Okay.
Fluorine, yeah. Fluorine has a 1/2 spin. And because fluorine has a 1/2 spin, it can couple. And not only that, because it has a very big coupling constant, you can actually see more than 3 bonds over. Okay, so that's fluorine. The chlorine, both the 35 and the 37, I don't think either one are spin active. So we don't see them at all. All right, so using the same pattern, we can start to solve much more complex structures than we saw on our first exam. And so we'll also be able to introduce new functional groups like nitro groups and other things like that. And what we'll see is we can do a lot more esters, and we'll see separation between the different sides of the groups on their esters, and adding some more amines, doing that odd mass rule as well. So are you getting comfortable with how to add NMR to the two things we already knew? Yeah. Okay. All right. So next week, we're going to go ahead and have an activity associated with this, and a little more of, and I'll assign homework for this as well. And then we will go ahead and get ready. Let's see what's after this. We're going to do NMR activity, and then a little more on NMR practice, and then we'll have a review in our exam on October 15th. That exam is going to have mass spec, IR, and NMR. And I will hopefully remember to cover up the empirical formulas so that you don't have them to start. I forgot. But, okay, and I will, well, the activity's on Monday, so I'll post it probably, I'm sorry, the activity is going to start on
Tuesday.
Thursday, so I will actually put it on Tuesday. So, but we'll go through a few more of these in class like this ahead of time. But then the activity we'll do on Thursday will have that, as well as I'll show you some of the homework problems and when that will be due as well. Because that'll be due probably next, not this Friday, but next Friday. Because it'll help you prep for the exam. Okay? All right, well, if anybody has any questions, go ahead and ask them. I'm gonna go ahead and stop sharing right here. And I will post this since we actually had like 2 or 3 people not show up. So you'll see this up on the web here in about 30 minutes.
I noticed when we were doing these problems adding the NMR, we kind of skipped over looking at hydrogen deficiency as a way of just kind of verifying our IR and mass spec.
Right.
Do you want us in the future, like when we're going to be on an exam, to include that?
Yes, and what we can actually do is the NMR actually helped jumpstart us a little bit, because what we can do is we can look at the NMR and say, oh, there's no alkenes and there's no aromatic rings. Therefore, I don't have to do the hydrogen deficiency index. But if you see an alkene or an aromatic ring, then you need to calculate your hydrogen deficiency to make sure that you have the right number of alkenes or the right number of carbonyls, like that. Because it was required because we didn't have any other structural information. Here we have additional structural information, so you might not need it all the time, but we'll use it like in the case if we had styrene, okay? Styrene, we would say, okay, we have these many carbons and this many things, and we have an alkene in the NMR, and we have a benzene in the NMR. So let's make sure we only have one double bond by calculating our hydrogen deficiency. Okay? So we will add it there, but it was really required before we added the NMR, because now we can see additional functional groups in the NMR, right? Maybe one in 5 questions, you'll actually have to calculate the hydrogen deficiency index now. Any other questions? Okay, great. Have a great weekend, and I'll see you people on Tuesday. Bye. Oh, I need to stop recording. That's what I need.